this video, we'll be talking about hardware. That's all the parts of your computer that you can touch. Hardware are the electronic components in your computer that process and store data according to software instructions. But before we get into that, let me once again remind you that you should be doing the required readings from your textbook before watching this video. This lecture will cover the first part of Chapter 4, Hardware. Software will be covered in a second video lecture that will also be posted this week. So that means Chapter 4 will be divided between two videos, just to make things a little bit easier to find. As with each week, there is also some recommended MyLab homework for this chapter, which should also be posted on this week's OWL tab. Let's get started by talking about a few emerging themes we see in computing hardware. First is that price and performance are always advancing. This means that computer hardware gets cheaper over time, but also it gets more powerful. Recall Moore's law, which we discussed in a previous lecture. This states that the number of transistors on a microchip doubles every 2 years or so, about every 18 to 24 months. In reality, this is more of a prediction than a hard rule. But so far, it's held true. Here we can see the transistor count in different integrated chips, namely CPUs. One thing to note here, however, about Moore's law, is that in many ways it's a self-fulfilling prophecy. CPUs and other integrated chip manufacturers use it as a benchmark for their progress and innovation. So it's not totally surprising that we see transistor counts following it. So that's great, but what do transistor counts have to do with computing performance, and what even is a transistor? Well, for our purposes, we can think of a transistor as a switch that can be controlled by the computer, sort of like a light switch the computer can turn on and off. These switches are used by the computer to accomplish two important tasks: processing and storage. They're also used for many other things, sort of like power regulation, but for our purposes, we're going to be mostly talking about processing and storage. Transistors can be used to form logic gates, which can make very simple Boolean decisions. These would be sort of true-false type logic calculations, similar to what you may have seen in if statements if you've programmed before, or used if functions in Excel. When we combine many logic gates, we can get more complex calculations, such as arithmetic. This is simple math operations like addition, subtraction, multiplication, and so on. Modern CPUs have billions of these transistors, which allow the computer to perform all kinds of calculations and process data. Transistors can also be used in storage. In simplest terms, you can use transistors to hold a simple on and off value, just like a light switch. We use these simple on-off values to create more complex data structures to store data in computers' RAM or CPU registers, or even things like solid-state drives, until it can be processed. We will learn more about this later in the lecture. What this all means for performance is that if we can fit more transistors on a chip, we can do more calculations faster and store more information. We see a similar trend even for non-transistor-based storage media, such as hard disks or even network bandwidth speeds. The cost of storage is dropping at such a fast rate that some predict that this cost will effectively be negligible in the near future. Cloud storage will essentially be free. I, however, am a bit skeptical of this claim, as our storage needs tend to grow with the storage capacity of our technology. As an example, Pong, one of the first video games ever created, only requires about 2 kilobytes of memory. However, nowadays, the Wikipedia page alone about Pong takes up 18 megabytes, which is about 18,000 kilobytes. Fitting more transistors on a chip also allows us to make technology smaller. For example, take this vacuum tube. To give you an idea of the size, here's a 3D printed banana for scale. This was the predecessor to the transistor, and used in early vacuum tube computers, which took up whole rooms. If you look at this thing, you can see why. This is just one vacuum tube, and hundreds are needed for even the most basic and simple computations. Shown here on the screen is ENIAC, an early vacuum tube computer that took up a whole room. Nowadays, CPUs have transistor counts in the billions. Imagine the size of a room you'd need to store a billion vacuum tubes. We also see this trend in storage media. This floppy disk that was still in use in the early 2000s could only hold 1.44 megabytes. Nowadays, we have micro SD cards like this one that can hold 1 terabyte. That would be the equivalent of about 700,000 floppy disks. This minimization does not just mean smaller phones. It means new possibilities. Being able to fit complex electronics in a small space has enabled things like wearables, such as smartwatches, 3D headsets, AR headsets, as well as Wi-Fi enabled IoT devices, like smart plugs and smart thermostats. It also means we can fit more processing and storage power into devices like phones, laptops, and tablets, where space is limited. The last theme is network is the thing. We are currently seeing the speed of computer networks getting to the point where they enable new applications and innovations. The last big one was streaming video, such as Netflix, or video conferencing applications like Zoom, that just would not have been possible 20 years ago. This has also made cloud computing a reality, enabled new cloud computing applications like cloud gaming. We'll get into this more when we discuss cloud computing in a later lecture. But the network is a thing does not just refer to the speed, but also the size of the network. Recall the network effect, which states that the value of a network grows with the number of participants in it. And at this point, the internet is used pretty much by everyone in any developed country. So enough with the theory, let's get right into it and start having some fun looking at the hardware components that make up your computer. What we can see here is a diagram that shows the basic hardware components of your computer. We can divide these into three types: inputs, outputs, and internal components. Inputs are the hardware that allow you to input data into your computer, such as a keyboard, mouse, webcam, or microphone. They can be external to the computer or built in like we see in laptops. Outputs are the hardware devices that output information from your computer, such as monitors, printers, and speakers. Again, they can be external or built in. Internal components are the parts we find inside the computer and do the job of processing the data into information based on software instructions. Let's start by taking a closer look at this whole setup. Okay, here we have a fairly standard desktop PC setup. We have some input and output devices over here, and we have the desktop PC tower here. This is what holds all the internal components. So let's start with the input and output devices. First, we have some fairly common stuff here. I'm not going to go too much into any of these because I'm sure you're familiar. We have a webcam. That would be an input device. It inputs both video, and some of them have microphones like this one. So it's inputting both video and sound. Next, we have an output device, some headphones. Headphones and speakers are both output devices that output sound. Then we have the monitor, probably the most common output device, and it displays graphics, as you're well aware. And we have our keyboard, inputs characters, and our mouse, which controls the pointer on your screen. These are all input devices. We're not too interested in the input devices because they're fairly standard, and I'm sure you use them already every day. So the most important part here is the actual desktop tower PC. And it's going to be the internal components that we're really interested in, but first we'll take a look at the outside. So on the front here, the first thing you might notice is a CD-ROM drive. So these could either read CD-ROMs, DVDs, or Blu-rays, depending on the type of drive they are. These are mostly input-only devices. You put the CD-ROM in, and you read the software off of it, or the music, or the video, and then you can access that on your computer. However, there also used to be CD-ROM writers. This is sort of falling out of style now in place of flash drives. But they were able to write to CD-ROMs, DVDs, or Blu-rays, depending on the type of drive you had. And they mostly tended to be a write-once system. So you'd burn the DVD once, and then it would be set. There were some read-writable ones that were multiple use, but the most ones we tended to see were just one write. These days, though, people mostly are using flash drives or SD cards, or just downloading things off the cloud. Also on the front, we see two audio ports, one just for microphone, one just for headphones. Under that, we have the USB ports. USB ports stand for Universal Serial Bus. They're sort of like a generic port that lets you connect all kinds of different devices. Most of the time, your keyboard, your mouse, your microphone, some cases, and your webcam all plug into things like USB. They could also be used for things like printers, scanners, pretty much any device. Even your cell phone could use a USB to communicate with the computer. Under that, we can see that this is a bit of an older PC. It has a FireWire port. It's starting to become more rare on PCs. It was basically Apple's alternative to USB. It's largely been forgotten about because USB-C is the superior standard. Let's take a look at the back. And talking about USB-C, the reason why it's starting to replace USB-B is because it has a lot more bandwidth in it. It can be used for more things. We can use it for video now, and use it for pretty much anything, even powering devices. So starting from the top, going down, on the back we see there's a lot more I/O ports, that's input-output ports. On the top we have input for power, that just goes right to your wall socket, and powers the PC. Pretty obvious. Down here we have rows of USB ports. Again, those are universal serial buses, and they can connect a variety of devices. We have another FireWire port, and we have an Ethernet port. So the Ethernet port is to connect to your network. So in cases where you don't have Wi-Fi, you might be plugged right into the wall for getting your internet. You'd go in through an Ethernet port here, and I would usually use something like Cat5 or Cat6 cable. And then we have some more audio ports for speakers, headphones, and microphones. And one thing I'll mention is you can see here we have two different video output ports. We also have the same ones down here. So what are these? So we have a DVI port here and here. This is, I think, a dual channel one. And we have VGA ports here. And we have an S-video port. So these are all older standards for getting video out of your computer to something like a monitor or a TV. Now, you'll notice that there's sort of duplicated. So at the top, we have the VGA and the DVI. We also have those down here as well. So what's going on here is the ones down here are for a graphics card, a GPU, graphical processing unit. And the ones up here are for the integrated graphics system from your motherboard. So these ones go to the graphics card. These ones go to the motherboard. So if you ever see a computer like this, and it has two sets of ports, one at the top here that looks like it's coming from the motherboard, one down here that's in one of these slots, you always want to use the lower slots, because that means it's going to be coming from your graphical processing unit. That means you'll actually get the better image faster and things like that. Usually on newer computers now, these are actually blocked off, so you can't use them that easily. So another thing to mention is these ports, as I said, were all older standards. Nowadays, we're seeing things more like HDMI, display video, and mini display video. I'll put an image of what those look like up here somewhere. Okay, moving down again, we have an eSATA port. So again, this is an older type of port that we don't see used as much often, but it was for connecting hard drives in a way that would be even faster than USB. However, with USB-C, it's sort of obsolete because USB-C can get those speeds without using a specialized port. So what I think we're going to see in the future is a lot of these ports disappearing, and they're all just going to be USB-C, which will be great. Sort of like what happened with HDMI back in the day, because a lot of these ports down here, like the VGA or the S-video, they actually couldn't output audio. And what a great development was HDMI, because it also included audio channels. So you only needed the one port. Back in the day, you had to have like a port for video, port for your left audio, port for your right audio, and so on. I think we're going to see something like that too with USB-C, because USB-C can also handle video. So what we might see, the future is just all USB-C, or something like rows of USB-B and USB-C. And we might even see graphics cards start to put USB-C only down here, because you can do USB-C right to a monitor. It basically supports everything, even powering devices, which is great. So enough of that. Let's actually open this thing up, then take a look inside. So one thing I should mention is if you're ever opening up a PC like this at home, you should use something called a static wristband. So what these do is they connect to your wrist and then to like the case or some kind of grounded source, just because on your own PC you don't want to damage it. And if you have static electricity, like from rubbing socks on the carpet or something like that, you could zap one of these components and it's not going to work again. This PC is just an old one that I found, so we don't really care what happens to it. But if this is your own PC, it could be expensive, you don't want to break it, make sure that you ground yourself in some way. So either be the best way is using a static wristband that would connect your arm to like the PC case. But another method is just to make sure you like touch PC case, just something that's grounded, some kind of metal, even a pipe, just to get rid of all that static electricity. So let's zoom into here and take a look at all these different components we have. So this is an older PC from 2008. However, most of the parts we see in here are going to be pretty much the same as what you'd see in a modern computer. The reason for this is most of the developments in sort of PC components have been substanding technology updates. That means they don't really disrupt the market, they don't change how it works, Instead, they're just like better improvements on it. So you might see better graphics cards, better CPU, better RAM, but you're not necessarily going to see something completely different in the PC. At least not yet. There could always be a disruptive technology coming. One example might be USB-C, how it's going to start replacing all those ports. So in here, the big board that we see, this whole thing here, the big circuit board that everything is on, is called the motherboard. Its main job is basically to connect everything and pass information between the different components. And don't worry, we're going to go into all of these parts in more depth after we sort of look at where they are located physically in the computer. So this big piece here that's sticking out right here is the graphics card. It's definitely an older one. The new ones look a little bit different. We'll take a look at that in a bit. Under this fan here is going to be the CPU, the central processing unit. And it gets quite hot, so it does usually have a heatsink of some kind on it, which usually has another fan. Here, we can see the RAM. These are usually in slots right onto the motherboard, and that's where we store the random access memory. So the main memory, that is volatile. And we will explain all that soon. Over here, we can see a hard drive. And up here is the back of the disk drive. And up here is the power supply, which brings power to everything. And you can see that it has wires that run into the motherboard, as well into some different components. On newer graphics cards, we tend to see them have a line right to the power supply because they're so power intensive these days. These red cables here are basically connecting the hard drive and the DVD, the disk drive, right to the motherboard. And you can see that we also have a case fan that pumps everything out. So most of those I/O ports that we saw before are all connected right on to the motherboard. And we can see here that these ones right here were the video ones that we saw that you shouldn't use because we have a graphics card. So you can see those right here are going right into the graphics card. You always want to use the ones going into your graphics card because the integrated graphics that come from the motherboard are going to be slower. So what I'm going to start doing now is start popping some of these components out, and then we'll take a look at each one individually and discuss it in more depth. And you might be wondering like how this actually goes together. Most of these parts are actually quite plug and play. They just sort of snap in. Like for example, these RAM chips just pop right out like that. And same thing with like cables like this. There's usually only one proper place for these to go in general. So actually building your own PC is fairly easy so long as you are confident that the parts are compatible. I'll just do a quick cut and get these parts out, and we'll start taking a look at them closer up. Now, I'm not going to go into too much depth on the input and output components of your computer, as I'm sure you're familiar with those from everyday use. Instead, I'm going to go and explore more of the internal components, starting with the power supply. The power supply has a simple job. It converts high voltage AC current from your power outlet into low voltage DC current that your computer can use. On the outside of the computer, the power cord would plug in here and go to your power outlet. On the inside, we get all these wires which take power from the supply to different components of your computer. None of your data is sent through these wires, just power to run everything. They have a standardized connector and a simple plug that will hook right into internal devices. An important consideration when picking a power supply is to ensure that it has enough power or watts to power all the components in your computer. Modern CPUs and GPUs can take a significant amount of power when operating at full capacity, such as when playing video games or rendering video. And you definitely don't want them to be underpowered when you're doing that. So you always want to make sure the power supply you select for your computer is adequate for your needs. Next up is the motherboard. This is the main circuit board in the computer which physically holds and connects the other components. If you think of a computer in terms of a body, this would be like the spine or nervous system, which allows the brain to send and receive signals from the rest of the body. Components like the CPU, RAM, and GPU tend to fit right into the sockets on the motherboard, while other components like hard drives and DVD players tend to be connected by a cable. The motherboard also provides input-output or I/O ports to connect various devices. Here we see some universal serial bus ports, or USB ports. These are one of the most common ports for connecting peripherals like keyboards or a mouse. There are also ports dedicated to other functions like sound and video. When selecting a motherboard, the most important thing is to ensure compatibility with other components. Not all components are compatible with all motherboards. The Central Processing Unit, or CPU, is the brain of the computer. It handles all the instructions from software and performs the computations. CPUs read instructions and values out of random access memory, or RAM for short, perform calculations on them, and then store them back in the RAM at a rapid rate. A CPU's frequency, or clock speed, determines how many instructions it can process per second. We sometimes call this the speed of the CPU, and it's measured in hertz. Modern CPUs tend to have a speed in the range of 3.5 to 4 GHz. That's about 4 billion calculations per second. The CPU I'm showing you right now is an Intel Core Duo, and it runs at about 3 GHz. Another thing to mention is that nowadays, your computer likely has more than one CPU core on the same CPU chip. We call this dual core if there's 2 cores, quad core if there's 4, octa-core if there's 8, and so on. Having multiple cores allows a computer to do multiple things at the same time. If you have 8 cores, you can do 8 calculations simultaneously. Now you might be saying, wait, I only have a quad core, and I can do more than 4 things at once on my computer. And you'd be sort of correct. What happens when you have more tasks than CPU cores is that your computer is actually rapidly switching between tasks to give the appearance or illusion of those things happening at the same time. Having more cores means less switching between tasks and a faster computer in many cases. Here I have an Intel Xenon CPU I pulled from an old server. Now, if we remove this metal shield that we call the lid or heat spreader, we can see there are 2 CPU dies embedded in this CPU. I've removed the top layer of a CPU die on the right-hand side, but the left-hand side is what they'd normally look like, sort of shiny like this. In this case, each CPU die has 2 cores embedded in it. That makes this a quad core. 2 CPU cores per each die, and there's 2 on one chip, making it quad. These CPU dies are small silicon wafers that consist of the circuitry and transistors that do all the processing. Now let's take a closer look at this die on the right that I removed the top layer from. Unfortunately, due to the reflectiveness of the glass coating and some scratches that occurred while I removed the top layer, we can't get too amazing a look with my microscope, but I do have a picture for reference of what a modern Intel CPU looks like, up close. All of these parts are incredibly small, barely visible with the naked eye. Moving on to RAM, as I mentioned, RAM is random access memory. This is like the computer's short-term memory. It stores the instructions for the CPU to run and the values for it to process. It also stores anything that has not yet been saved to the hard disk. For example, if you're typing out a Word document but haven't yet saved it, that document is in the RAM until it's saved. RAM is volatile memory. This means that as soon as the computer loses power or is turned off, everything in the RAM is lost. And you may have experienced this before. Perhaps you are working on an essay or a report in Word, and suddenly the computer restarts or you lose power before you can save. When it turns back on, your work is all gone. Why? Because it was only stored in the RAM, and RAM is volatile, meaning that its contents are lost as soon as the computer is restarted. Only once you've saved the document is it stored on the hard disk in non-volatile memory. The point of RAM is not to be permanent storage, but to act more as a waiting room for instructions and data to stay until the CPU needs them. You might ask, why have RAM if we have a hard drive that's non-volatile? That means it keeps its memory after you restart. Well, RAM is significantly faster than your hard drive, or even a solid-state drive. And the CPU needs that fast access to instructions and data to actually run at its full speed. If we're reading instructions directly from the hard disk, the CPU would have to spend most of its time waiting for instructions rather than executing them. The main considerations when choosing RAM are the capacity, that is the amount of memory it has, and its speed. More memory means the computer can hold more values and instructions before having to read from disk, which can make it faster. Similarly, faster RAM means that the CPU can get instructions faster, speeding up the computer yet again. Next, we come to the GPU, or the Graphics Processing Unit. The GPU is a dedicated processor just for manipulating graphics, images, and videos. They have their own built-in memory and processing unit. For home users, the main use of the GPU is video games and video playback. However, they also have uses in business for things like video editing and rendering, and 3D modeling, and computer-generated graphics. And in some cases, they can do specialized computations faster than a CPU. One such example would be mining cryptocurrency, or certain types of machine learning. Shown here is an older model GPU. Newer ones are bigger and look something like this. Shown on the screen now is an RTX 3080. It's a GPU by NVIDIA, aimed at home users, typically for gaming. NVIDIA and AMD are the largest GPU manufacturers for the home market. Next, we're going to talk a bit about storage. This is the non-volatile memory used by a computer to store programs and data long-term. In the very early days of computing in the 1950s, the main storage device was punch cards, like this one here. This stored data or program instructions by punching holes in the cards. The location of the hole determined the value of the byte or the character. A standard punch card stored about 80 bytes. This would be about one sentence if you're lucky, or maybe one line of code. Whole boxes of these cards would be needed to run just a single computer program. After punch cards, the next popular storage method was magnetic tapes. In business and industry, these were often really massive large reels full of magnetic tape that could be read by the computer. With the birth of the personal computer in the 70s, we saw home storage done on magnetic cassette tapes. These were often the same types of tapes that were used for music. You may have seen them before. But instead of music, data was encoded on them. Early home computers did not have any internal storage, so cassette tapes were the only way to add new programs or store any data. By the end of the 70s, we saw a rise of the floppy disk. The first floppy disks popular with the home market were 5 1/4-inch floppies, like this one I have here. This one has a copy of MS-DOS. At least it's one of many disks that you'd have to run for your computer to get a copy of MS-DOS. And they're called floppy because they have a little bit of a bend to them, and also because the internal disk inside of them was also floppy. These stored about 120 kilobytes, or about the equivalent of 1,500 punch cards. Next, we saw the rise of the smaller 3.5-inch floppy, which ironically was not floppy at all. It has a hard plastic casing on the outside. However, the internal magnetic disk is floppy, like the larger size. Anyway, despite being smaller, these guys could store 1.44 megabytes, or the equivalent of about 12 5.25-inch floppies. By the end of the 70s, we also started to see internal storage becoming common in home computers, and that brings us to hard drives. Hard drives are currently the most common storage method that we see in computers, and they have the advantage of being cheap and they can hold a lot of data. When picking a hard drive, the main considerations are capacity, that's how much it can store, and speed, how fast it can read from the disk. Modern hard drives can go all the way up to 20 terabytes, which is about 14 million 3.5-inch floppies. One downside of hard drives, other than being slow, is that due to their moving parts, they're very vulnerable to physical damage when dropped or hit, as the disks are glass. The read-write head touching the surface of the disk, even slightly, can also cause significant damage and data loss. Here we have a fairly standard desktop hard drive. This one stores about 1 terabyte, but this is actually starting to get a little bit small these days. More commonly, in most computers, we see around 2, 5 terabytes, but they do go all the way up to 20 terabytes, as I mentioned. There's also a different style of hard disk for laptops, and it's just a little bit smaller to fit that form factor. So you might be wondering what's going on in these hard drives. And I have a laptop hard drive right here that I've already moved top on. And you'd never want to do this to your own hard drive because any kind of speck of dust or even a fingerprint on this platter here would make it unusable and you'd lose any data on it. However, for us, it does give us a good look inside, and this is already a dead hard drive, so no big loss. And what we can see is this really shiny glass platter. And this is a magnetic platter where all the data is stored. The way this works is this spins really fast, faster than I could spin with my finger, and this read head goes back and forth to find the sectors on it that you're looking for. And it can also write to it. On the tip there is a little magnet that it can control to either read data or write data, and that spins really fast. Now it's hard to see in this, but there's actually a stack of multiple platters. So it's not just this one platter, there's also one underneath it, and one, sometimes on bigger ones, there's even one underneath that. And there's another head that goes underneath the disk. Back and forth like that. Solid-state drives, or SSDs, are becoming more common as they bring the advantage of far faster read speeds. The downside is that they have a limited number of writes before they die, although there's been a lot of work in this direction towards improving this. They also tend to cost more per gigabyte than hard drives, and because of this, we often see hybrid approaches taken in computers, where a computer will have both an SSD and a hard disk. Normally in such a setup, applications and the operating system are stored on the SSD, while documents and media are stored on the hard disk. So for example, you might have like your movies, your photos and stuff on the hard disk, while you have like Windows on the SSD and your games or things like that need that fast read speed. The size of SSDs can also go all the way up to 100 terabytes, though we don't see that normally in the home market, and that's about 5 times larger than the largest hard disk. However, these very large SSDs, as I said, are not aimed at home users, with prices in the $20,000 to $40,000 range for those massive ones. Ones aimed at home markets tend to be in the 1 to 2 terabyte range, and they're far more reasonably priced. So what I have right here on the screen right now is a solid-state drive. As the name sort of implies, it's solid, there's no moving parts, it's just a chip with some memory modules soldered onto it. And the idea here is that this is a non-volatile way to store information and data, just like a hard disk, except we don't have those spinning platters or moving read head, so it can be more reliable, and as well as faster. And these just sort of plug right into your motherboard, and then you screw them down. Another storage method is optical discs, such as CDs, DVDs, and Blu-rays. These are all starting to die out and become obsolete. Most PCs and laptops no longer even come with disk drives. However, they can still occasionally be found in use in some places and businesses. So what I have here is an example of a CDR. This is a CD-based storage media. It can store about 700 megabytes. And the way this works is the disk drive has a laser that actually reads little grooves inside of it. So if it's used like a dot, that might be a 1, or a no dot, there might be a 0. And these tend to come in writable or non-writable formats. So if you buy software on a disk, they're usually not writable. This one here is a CDR, which means that if you had a proper disk drive that can write to it, you would be able to store data on it. Most of these tend to only store once, and then you're done. You only get one write. Though there were some RW versions that were able to be rewritable a few times. Optical discs have different sizes depending on the generation of the technology used. CDs have about 700 megabytes, DVDs about 4.7 gigabytes, and Blu-rays about 50 gigabytes. All significantly less than hard drives, but they have the advantage of portability and being cheap. That brings us to a more modern equivalent, flash drives, also called USB keys. These are essentially portable solid-state drives that can be plugged right into a USB port. They tend to be slower and smaller in capacity than SSDs, but they have the advantage of portability, and they tend to be far cheaper than an SSD. As with SSDs, they have a limited write life. I won't say too much about these as you're probably pretty familiar with them. The last storage method I'll mention are SD cards. These come in a few varieties, but most common are SD and microSD. They're commonly used in cameras and phones due to their very small size. SD cards can go up to 1 terabyte in size, which is impressive since they are smaller than a fingernail. Currently, larger capacity cards are being developed, and we'll likely see 2 terabyte or even higher SD cards in the very near future. Just like with other solid-state storage we spoke of, these are non-volatile but have limited lifetimes in terms of number of writes. When buying SD cards, it's important to consider not only the capacity, but also the speed, as there's a wide range of supported speeds. For example, using a slow SD card in a gaming console could lead to long load times. Here we have an example of an SD card. This one's only 16 gigabytes, but as I said, they do go up to a terabyte. And SD cards are the type you tend to see used in like cameras and things like that. And here we have an example of a micro SD card. This one's only 4 gigabytes, but they also go up to about a terabyte. And this would be something you'd see more in like a phone. And that's pretty impressive, a terabyte, considering that it is only about the size of your fingernail. Back in the 70s, this would be like stacks and stacks of thousands of floppies. As an alternative to actual physical storage, that's a component in your computer, we're also seeing a move to cloud storage. These are services that allow you to store files remotely on the cloud. We'll be getting more into cloud computing in Chapter 6. However, this means that we are storing our files on a remote server somewhere in a cloud provider's data center. These files can only be accessed over the internet, but so long as you're connected to the internet, they're accessible seamlessly on your computer, just as if they were stored locally. This has the advantage of not having to purchase storage hardware, and is often cheaper per gigabyte than like a hard disk. It also means that the cloud provider has to deal with and maintain the infrastructure for doing backups on their end. This doesn't mean that you don't have to worry about doing backups at all, just that the data is less likely to be lost than if it were stored on a traditional hard disk. Cloud storage solutions include things like Dropbox, Microsoft's OneDrive, Google Drive, and Apple's iCloud. The downside, besides always needing to be connected to the internet, are the potential privacy and security issues. You're providing all your files to the cloud provider, and this could be a problem if you don't trust them with your sensitive documents. Even if the provider's not intentionally malicious, they can be a target for attacks. If they have a data breach or hacked, your files could be stolen. And this could also apply to your account, personally. If attackers, for example, guess your password or trick you into revealing it. For example, take the case of this Apple user who was storing their cryptocurrency wallet in the iCloud. Hackers tricked them into revealing their credentials for iCloud, and they ended up losing over $650,000 in cryptocurrency. So the important message here is only store the files on the cloud that you can risk being revealed to an attacker. And moving on now to types of hardware. And by types of hardware, I mean the different formats we find computers and computational devices in, such as personal computers, tablets, phablets, smartphones, and servers. Let's take a look. Okay, here in front of us is a wide variety of computing hardware. Let's start with a PC, or personal computer. I assume you're already fairly familiar with personal computers. This category of computing hardware would also include Apple desktop computers. These are general-purpose home computers that are not portable, but tend to be cheaper and more powerful than the portable alternatives. To some degree, these are being supplanted by tablets and smartphones, but I think it's unlikely that we'll ever see them totally replaced due to use in business, gaming, and just the improved productivity they offer. For example, think of trying to type a thesis on a tablet. It's not just going to end well for your fingers. Laptops are essentially a portable version of a PC. They have similar hardware and run the same software, including the same operating system in most cases. But they also have a battery and a screen attached to them, allowing them to be used on the go to some degree. Laptops tend to cost more and be less powerful than PCs, but you have that added portability benefit while still having a full computer. So if you take a look at this, I'm sure you've seen laptops before, but they have the same sort of I/O ports that you'd expect from a PC computer, but there's fewer of them. So on the back here, we've got power in, we've got our HDMI, we've got our Ethernet, and on the side, we have some USB ports, audio, and things like that. Depending on the laptop manufacturer, you might get more or less. I know Apple, for one example, tends to try to minimize the number of ports and replacing them with just USB-C, but other manufacturers are still putting things like HDMI and those audio ports in. The next type of computing hardware we're going to take a look at are smartphones, like this guy here. This is a Samsung smartphone. It's fairly typical of what you see for smartphones these days. It runs an Android operating system. The main I/O is going to be for the touchscreen. Your touch is the input, and the output would be the graphics. But it also has things like camera and speakers, microphone, pretty standard. One of the key differences here is it's not going to have many I/O ports, sort of like your laptop or your PC. Usually you get like one USB-C or one micro USB, as well as an audio jack if you're lucky. So if you're not familiar with the history of smartphones, before we had smartphones, we had just normal cell phones. I guess you'd call them dumb phones. And basically all they could do was make phone calls and send text messages. Maybe you'd be lucky and get like a little snake game on there, but they're pretty limited. So the reason why we call these smartphones is they're sort of the next upgrade from that. They have expanded processing capabilities and the ability to run software applications, like you might have your Uber app or Skip the Dishes app or things like that. They tend to run more limited operating systems than what you'd find on a PC or a laptop, and these would be operating systems like Android or iOS. They're also really important for business, not just personal use, because they allow business to be done in a different way, portably and on the go. They also offer the opportunity for businesses to develop apps to provide new kinds of services, sort of like Uber does, or things like that. So next, we're going to move on to tablets. So I have two different tablets here. We have a smaller Samsung tablet, and we have a larger Amazon Fire tablet. However, they're both essentially the same in the operating system. They both run a version of Android. Amazon tends to customize theirs a bit more, but they are both Android under the surface. And just like smartphones, they have touchscreen as the main interface. In fact, you can really think of these tablets as sort of just like a really big version of a smartphone. The only real difference is that smartphones tend to have something that we call a cellular modem in them. That means they have the capability to make phone calls and send text messages. Well, that's usually an optional feature on tablets. It also means things like smartphones can use the cellular network to access the internet, while tablets are usually more restricted to just using Wi-Fi, unless they have that option of having the cellular modem built in. So they come in a variety of sizes, but essentially they're big smartphones, and they run the same sort of operating systems that smartphones do. That would be Android or iOS. So iPad would be an example of one that would run iOS from Apple. So the next home computing hardware we should talk about, and unfortunately I don't have an example of one with me today, are phablets. And that word sounds a bit funny, and it is, but it is the combination of the words phone and tablet. And the idea here is it's just a smartphone, essentially, that's a bit bigger than what you'd normally see, so big that you may have trouble getting it in your pocket unless you have big pockets. And it usually comes with a stylus, so you can sort of write notes with the pen-like object on it. And this really came about from Asian markets where there's a big demand to have both tablets and phones, but consumers didn't want to buy both. They just wanted to buy one thing that did both. So tablets were born. The idea is that you get the best of both worlds. You get the tablet and stylus, and you get the cell phone for making calls. Fortunately, sometimes it's also the worst of both worlds, because now you have a phone that you can't really fit in your pocket. So the next big category of computing hardware, and I don't have one on this table right this second, is servers. And these aren't aimed at the home market. Instead, these are aimed at like data centers and server farms. And these are computers that are heavily optimized for performance and uptime, reliability. So the idea here is you basically strip everything out that's like usability, graphical interface, aesthetics, and we just want pure functionality, pure speed, and pure reliability. We want it to keep going as long as it can, and we want it to, if it has like some kind of hardware fault, that there'll be some sort of redundancy, so we could fix it easily without even causing much downtime, and we want it to be as fast as possible at the cost of not being necessarily as usable as something like a computer, like a desktop computer, or a laptop computer. Now, I don't have one here, but let's go try to find some servers. Hi class, I finally managed to find a server rack that you can see behind me. Fortunately, most data centers aren't really happy with random professors walking around in them, so we'll have to make do with this rather old and neglected server rack I have behind me. So most servers that we find are going to be in data centers or data farms, and they are stored in racks like this, though a little bit more impressive and newer. And that's just to keep them all in one spot, so you can do things like backups, air conditioning, cooling, backup generators, so everything you need like that in one spot. It also keeps them nice and stacked and in one spot. So let's have a look. So here you can see a server rack, an old one, but it is a server rack. And the idea here is it's just basically a big cage that we can stack servers in a safe way and keep them in one compact space. Let's open it up and have a look. So up here we have all of the networking equipment. This would be things like routers, switches, and just general ports that we can plug in if they're running to different places in the building. Down here we have the actual servers. So each one of these little rows, like this, is its own server. That means this is basically a powerful computer, a bunch of them stacked right on top of each other, and they would run server application software, such as web servers, video game servers, pretty much any kind of service you can think of that you'd access through a browser or through the internet. Now, right now I have all of these turned off. They are quite noisy when they're running. It's actually so loud that you'd usually need some kind of hearing protection in a real data center. Let's turn them on and see what that might sound like. So let's turn them on and see what that might sound like. Got a few lighting up. Starting up. So I'm not sure if you can hear me right now, but it is getting quite loud. And that's just with one running right now. Let's power up a few more. Okay, we have a few of them going. And just because it's so loud I can't talk, I'm going to turn them off now. Generally not a great way to turn off servers, but these ones are sort of old neglected ones, so we don't have to worry about shutting them down too safely. So these servers might look quite different than what you're used to seeing on your home desktop computer or maybe a laptop. Instead of being aesthetically pleasing or even functional for the end user, they are purely aimed at performance and reliability. So that means they have a lot of redundancies built in. So for example, you can see these black little levers here. And what these are is an easy way to pop out the hard drives. So you could do this and just pull a hard drive right out. And the reason why they have a feature like this is that you have two hard drives. They're set up in a RAID configuration, which basically means that if one of these hard drives fails, you could pop one out and put in a new one, and it would copy over the data from the other one with almost no downtime. So a lot of the stuff we see in servers is built around redundancy. That means making sure it's going to keep up running when something fails. So another thing that's cool about these is that they're very easy to do maintenance on. It might not look like it because they're all stacked up like this, but if we undo these little knobs here, we can see that they actually completely slide out all the way. A little bit more perspective on that. And you can even easily open them right up and get right into the hardware. So if you had a server that was down, you could unplug it, pull it out, and replace any component you need, and slide it back in. And be back up and ready to go right away. So real data centers have many other protections to keep servers safe and running, such as backup power generators, multiple internet connections, specialized fire suppression systems, and air conditioning systems. Many big companies also have multiple data centers spread out around the world to provide even more redundancy and more spread out computations to be closer to the end user. Ideally, an end user would connect to the closest one near to them to reduce latency. So once again, many layers of redundancy to keep these things up and running. So let's take one of these servers back with us and have a better look at some of the hardware going on inside. Hopefully they won't mind. And we're back in the studio, and I have one of those servers from the rack we just saw right here. One thing I wanted to do is open it up, take a look, and see how it's different than some of that desktop PC hardware we saw. And one of the first things you might notice, or at least one of the first things I noticed while lugging it up several flights of stairs, is that it is significantly heavier than a normal desktop computer. Part of the reason for that is the all-metal case around it, quite thick metal, as well as it has a lot more components inside, because it has a lot more redundancy. Before we get it open, let's take a look at the front and the back and see what we can see. So on the front here, we can see that we have some USB ports, pretty standard. We have also a VGA out. So you might be wondering what that's about. Kind of weird to have the VGA plugged right into the front of the server. The idea behind this is that this is for when you're trying to debug something, something's gone wrong on the server. You'd hook in a monitor that's either on a cart or built into the rack and be able to view the terminal from the server and see what's going on. In most cases, you're not going to be getting a GUI for that. It'll just be sort of like a command line. That's all text-based. Also on the front, you'll notice that we have a DVD player. So this is a bit unusual these days. More so we see just USB or USB-C these days. The idea back when this server was made is that the operating system and some other software you might need on the server would come on disks, so you needed a way to easily load that in. The other thing we saw when it was still on the rack are these two hard drive spots right here, and they do open up. And you can get the hard drive out. And the idea behind this is simply that these are hot swappable, meaning that you can pull one out as the server is actually running and put a new one in if it fails. And in theory, if you have it set up correctly or in the right RAID configuration, it would copy everything over and be ready to go in a few minutes. These back in. Another interesting feature we have on the front here is this little power button. But it's not just the power button, what's beside it. And we have a little LCD display, and this is a convenient way of seeing what servers are in an error state. If something's going really wrong, that can be detected by the server. This will change color and display an error code. This just lets you really quickly find that server on the rack and deal with whatever error it is. When we're looking at the side, there's also one interesting thing here, and you can see these little screws that are poking out, as well as the screw at the front. What these are is how we mount this to the rack. Because all those servers, as we saw, were stacked in a rack. These screws just provide an easy way to mount it onto that rack. Moving to the back, we can see a few features, or mostly I/O ports rather. We have a console I/O port and another VGA port. So we have a VGA port on the back. This is usually harder to get to in a server, but in some cases you have something called a KVM switch, which lets you view what the video output is on different servers, all connected to one monitor, and you can sort of switch between them. The console port is a type of serial port looking thing, and what it does is it allows you to access the console in another way. And that works both ways. You can also send input into that port, as well as gets the console out. On the back, we also see some USB ports, pretty standard. And interesting thing here is we see two Ethernet ports. Again, this is all about redundancy. So you might have one plugged into one internet connection and one plugged into a different internet connection. That way, if one goes down, your server can still be connected. And moving on, we see a little status light. So if you're looking at it from the back, you can also see if there's an error status. And what's really interesting here is that we see multiple power inputs. So this is the exact same sort of port we saw on the desktop computer, except now there's two of them. That's, again, redundancy. So you could have these hooked into two different power sources, and if one of those power sources died, you would still have power. Similarly, if one of these power supplies died, because there's two full complete power supplies in here, you could still be going. And there is something else special about them. These are also hot swappable, meaning that you can pull them right out, and you get the whole power supply there. There's two of them, both can be swapped out. So if one of these stopped working, you could pull it out, put it back, a new one in, and the server won't even shut down, because as long as it has one, it's still going. So again, we see redundancy. That's the key here. Okay, let's move back onto this side and actually open it up. And we can start taking a look inside. So the first thing we'll see is that everything's sort of laid out quite differently than what we saw in the desktop PC. The reason for that is partly because everything has to fit in this rack form factor. It has to be in this skinny little box. Another thing we'll see is that everything is quite modular. We're trying to make it very easy to swap things out. What we see here, all these rows of things, are all fans. So each one of these has two fans. And a big thing here is the cooling for servers, because we don't just have the issue of the CPU generating heat, we also have the issue of all those other servers generating heat. They're all stacked together quite tightly, so heat is a big consideration. So cooling is very important, so we see quite a lot of fans, and this is the reason why they were so noisy when we turned them on. And these are pretty hot swappable too. You can pick them up and take them right out, and then swap them in with a new set of fans if you need to. Now, all the interesting stuff is covered in some of this plastic, so we'll open that up now. Well, that's just a plastic cover to keep everything protected and stop it from shorting on the top of the server case. So we'll see some interesting things in here. First of all, there is a lot of RAM. So we have a lot more RAM slots than we would normally see on a desktop PC. And the reason why that is usually servers are going to want them to have like higher specs. So we need spots to put in a ton more RAM. Open up one of these. Take the RAM chip out. The RAM is fairly similar to what you would see in your desktop PC, except the difference is it's more industrial quality and it has more error correction capabilities than what you would have in your desktop PC. See, there's quite a few sticks here. Next, what we'll see are these big pieces of metal. What these are heat sinks for the CPU. Let's open this up. I'll just open up one for now. You can see the thermal paste is quite old on this one. It needs to be replaced. And down here is the CPU socket with a CPU inside of it. Let's see if we can get it out. And once again, something I should mention is if you're ever opening something like this up, you should be using a static wristband of some kind. So we have a CPU. It actually looks quite similar to the desktop CPU. Big difference here is it is a server style CPU. So it's a different line from Intel called Xenon, which has a little more features than you'd get with a standard desktop CPU. They tend to be more expensive, but also more powerful. And we actually have two CPU sockets. So on the desktop motherboard, there's only a single CPU socket. The server has two. So that means we can sort of, in addition to having one CPU that has multiple cores, we can also have two CPUs with multiple cores, even more. Now, servers these days can even go far beyond this and have quite a few more sockets and have quite a significant number of cores. So there is something missing, though, that we would expect in a normal desktop PC. So let's go over some of the parts we have here and see if we can figure out what it is. So these are our power supplies, the two of them that are hot swappable. Here we have our RAM, we have our CPUs, we have fans, we have the hard drives that are in these bays, and we have sort of the general motherboard. It's a bit bigger and more spread out because of the form factor and all the extra hardware. But there's a component that we saw in the desktop PC that's not here. Can you guess what it is? Okay, so what did you think it was? And the thing that's missing here is a graphics card, or a GPU. So I can show you quickly again. This was our GPU from our desktop computer. It's a bit older one, but it had one. And there's no GPU in here. At least there's not a dedicated GPU. The motherboard has some really primitive integrated graphics, but we don't have a GPU. Now, the reason for that might be somewhat obvious, is in general, your server is going to be focusing mostly on tasks like serving web pages, processing data, things like that. It's not worried about displaying graphics to the end user. So in most cases, there isn't a need for a dedicated high-powered GPU in servers like this, like there is on a desktop PC where you might be doing things like video editing, playing video games, rendering 3D models, things like that. There's an exception to this, though, however. So in some of the more high-powered servers, we do see spots for multiple GPUs. And the reason for that is that in really high-performance computing, sometimes GPUs can be used for like crunching numbers, data processing, things like that, as opposed to like playing video games or video editing. Some cases would be like mining cryptocurrency, or some AI tasks benefit from GUI processing. That would be a different kind of GUI processing that what you'd be doing on your desktop. That'd be more focused at scientific research, cryptocurrency, things like that, as opposed to like playing video games. One last thing I should mention is something you'll see here is the motherboard is quite bigger. It's more laid out like this, and that's because it's far more modular. So over here, we have like controllers just for hard drives, and they could be swapped out without replacing the whole motherboard. We also have like a daughter, and usually what these are called when you have little boards that sort of aid the motherboard, these are called daughter boards. And they provide some dedicated tasks. With this one over here, handles the hard drives. And that sort of breaking it up more means that you only have to replace the one daughter board instead of the whole thing if something goes wrong. This also has to be laid out a bit differently because we don't have power cables running everywhere. Instead, the power is going right into the motherboard directly, and that then feeds it on to everything that needs it. We also need a lot more room, because we have a lot more room for RAM, we have a lot more room for CPUs, a lot more room for fans, things like that. So the big takeaways here are that servers are different in that they're dedicated to performance, they're optimized for performance, so they're going to have spaces to put in more computing power, multiple CPUs, way more RAM sticks, things like that. And they're also going to be really big on reliability and uptime. So we see a lot of redundancy, like the multiple power supplies, multiple hard drives, all kinds of things like that. And we also see a lot of things that are modular, making them very easy to pop out and replace if something goes wrong. Now we've looked at this specialized server hardware, but a key thing to keep in mind is that the main difference between a server like this and a PC in your home is not actually the hardware, but the software it's running. All of these hardware differences are to keep the server up and running and get the most performance possible. However, at the end of the day, it's just a computer and could potentially run the same software as your home PC. The reverse is also true. In most cases, you could run server software on your home PC. Might not be a great idea, but it is doable. You could start running into issues like downtime, not very reliable. But what a lot of programmers do and people working on software that's eventually going to be on a server is to start developing it on things like desktop computers, get it ready for production. That's like actually putting it on the server. And once it's actually ready, then they go out and put it on a server. Reasons for that, it's a lot easier to develop on your own local machine than sort of uploading back and forth between a server, as well as there are costs associated with running things on a server. You either like own your own data center, in which case you're paying for things like power, you're paying for people to keep it running. So using a server just for development might not be the best idea. And the other issue is that if you don't own the data center and you're just renting space from someone else, you have to pay for that server time you're using. Anyway, we'll talk more about software and what difference between like server and application software more in our next lecture. But for now, we are going to get back into talking about hardware and some of the innovations that we've seen with it. And we're back. So the key takeaways here are that servers are sort of like PCs on steroids. They're optimized for performance, and they do this at the cost of usability and a different form factor. So while there are differences in hardware, the biggest differences are on terms of software, what they run. But looking back at hardware, they do tend to have more redundancies built in when we're talking about actual professional servers that you'd find in a data center. So that'd be things like multiple hard drives, multiple power supplies, multiple Ethernet ports, things to keep things running in case something goes wrong, and to make maintenance easier. Now we'll move on to talking about how computers store and represent data. So we spoke earlier about how transistors are used to store information in the computer. For example, in the RAM, in the CPU registers, in the CPU cache, or even in solid-state media. But we didn't really say how they do that. We did mention that there's sort of like an on and off switch the computer can control, or maybe like a light switch they can control, but we didn't say how that translates into actually storing something. So let's think a bit about how we might be able to do this and try a few different approaches. In this case, let's say we want to just store a positive number. So I think the first approach people might have, if they're said like we have these 4 lights and we want to store some number, we might say something like however many lights are on is the number that we're storing. So if we had 1 light on, we'd say the number's 1. If we had 2 lights on, we'd say the number's 2. If we had 3 lights on, we'd say the number's 3. And if we had 4 lights on, we'd say the number's 4. So it's not a bad approach, but it's going to have problems. What if we wanted to store the number 1 billion? We would need 1 billion lights. And it's not really efficient. And if I was doing this in person, I'd have like lights all the way out across multiple rooms. The other problem is we have to have all the lights on to store that number. We're using a lot of power there. So maybe there's a more efficient way we could try. So what if instead of doing that, we gave each light a number, and we said if that light's on, that's the number it represents. So we could say that's light 1, light 2, light 3, and light 4. And if light 1 is on, we'd say the number's 1. If light 2 is on, we'd say the number's 2. If light 3 is on, we'd say the number's 3. And if light 4 is on, we'd say the number's 4. So there's a slight improvement here in that we don't have to have all the lights on to store the number. But if I wanted to store the number 1 billion, I'd still need 1 billion lights. So maybe there's a more intelligent way we could do this. And this is now getting into how computers actually store information. And the way this works is instead of just numbering them 1, 2, 3, 4 going on, we can number them a little bit more intelligently in such a way that we could add them together and always get a different number. So the way we would do this is start with 2 to the power of 0, then 2 to the power of 1, then 2 to the power of 2, 2 to the power of 3, and if we had more lights, it would then be 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and keep on going all the way until however many lights we had. And this would equal, in this case, 1, 2, 4, and 8. Now, these numbers aren't chosen arbitrarily. They have a special property, and that is, however many of these numbers you add together, you'll always get a different number. But not only that, there'll always be a possible combination of these numbers to equal the number you're looking for. So that might sound a little bit confusing, but let's see how this works if we wanted to count using this system. So to get number 1, we just turn on 1 light. Remember, we're adding them together. So whatever the light is on, whatever lights are on, we add those numbers together. So we start with 0, and we turn on light 1, so we're adding 1 to 0, and we get a 1. Now, if we wanted to get a 2, easy enough, we just turn on light 2. 0 plus 2 is 2. Now here's where the things get interesting. Now we want the number 3. Now there's no 3, because we went 1, 2, 4, and then 8. So there's no 3 light to turn on. Instead, we turn on lights 2 and 1. 2 plus 1 is 3. So that's how we're sort of saying we're storing the numbers. We're saying we're add those together. Now if we wanted 4, that's going to be easy enough. There's a 4 light. If we want 5, then we turn on the 1 light. So 4 plus 1 is 5. To get 6, it's 4 plus 2. To get 7, it's 4 plus 2 plus 1. To get 8, we just turn on the 8 light. To get 9, we turn on the 8 and the 1 light. And so on in this pattern. So you see what happened here is just using 4 lights, we can store the numbers from 0 all the way up to 15. So in total, that's 16 numbers with only 4 lights. And this is how computers do it. However, we usually don't talk about it in these terms. Instead, we usually talk about it in something called binary, which is a different base system that sort of stores numbers as only zeros and ones. So the way we think of this is we can say if the light is off, it's a 0. If the light is on, then it's a 1. So in computers, it's not quite that simple. It's more like if this transistor has a high voltage output, then it's a 1. If the transistor has no voltage output or a low voltage output, it's a 0. So there's no actual zeros or ones in the computer. It's just a circuit that's energized with voltage and one that has low voltage. But it's the exact same concept. And the sort of the model we're using to store data, at least theoretically, is the zeros and ones. So let's look at this again, but overlay those zeros and ones. So here we see the number 11, the 8, the 2, and the 1. So all the lights that are on would be 1s, and all the lights that are off would be 0s. So a 1 means that you add that number, the 1 in this case, and a 0 means you ignore it. So to get 11, we added 8 plus 2 plus 1. So to go the other direction, from a binary number to a decimal number, which is what base system we use, you would say that we write out the number, and you write these other numbers underneath it. So remember, you start with the power 2 to the power of 0 to the power of 1. So however many lights you have, or how many digits you have, just keep going with the powers of 2. And whenever there's a 1, you add that number. And if there's a 0, you ignore it. So in this case, there's a 1 with the 8, so we add in the 8. There's a 0 for the 4, so we ignore that. There's a 1 for the 2, so we use the 2. We're going to add the 8 plus the 2. And there's a 1 for the 1, so we use that 1. So whenever the light's on, there's a 1. Whenever the light's off, it's a 0. And this is how we can sort of convert back and forth between those numbers. Now for this course, I don't expect you to understand or be able to do binary to decimal conversions, just sort of have an idea, like a high-level concept of how this is happening in the computer. So let's try to put that into practice. Here I have a binary number, 1101. So using what we just thought of, can you convert this into a decimal number? That's sort of a decimal in the base 10 system we use. So I'm going to give you a timer to think about it, but remember you're just writing the numbers under it. So 2 to the power of 0, 2 to the power of 1, and so on. And you add together where there's a 1, and you ignore it where there's a 0. So let's give that a try, and I'll be right back. Okay, and we're back. Hopefully you have a solution that we can check. So we start by writing the numbers under it, and these are those bases of 2 that we just saw before. And wherever there's a 0, we ignore it, and wherever there's a 1, we sort of add it to our total. So our total here would be 8 plus 4 plus 1. We get rid of that 2, and we add the 8 plus the 4 plus the 1, and that's equals 13. So this binary number is equal to 13 in decimal. So now I know this might be a little bit confusing if you're new to the concept, but for the purposes of this course, you don't have to know how to do these conversions. I just want you to have sort of a high-level understanding of what the computer's sort of doing behind the scenes, how we're actually storing these things. So on a test or a quiz, I'm not going to say convert this number, but I might ask how computers store it. And that's a sort of a high-level concept. So as a quick summary here, there's a table of the first 15 decimal numbers and the first 15 binary numbers. And there is a bit of a pattern here that you can notice, and it's the same pattern we use in counting in decimal. So you can see in decimal how we go all the way up to 9, and after we get to 9, we sort of start over again, but with like a 1 in front. It's the exact same idea in binary, except we only have 2 numbers, a 0 and a 1. So the first number is 0, the next number is 1. After that, we have no more digits to use, so we have to put a 1 in front. Then it becomes 1, 0, then 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, and so on. Again, you don't have to memorize this table at all. I just want you to have sort of a high-level understanding of what's going on here. So you now might be asking, well, okay, I can store a number, but how do I store text, characters, digits, things like that? Like if I write an essay, how's the computer storing that? Because there might not be that many numbers in my essay. Well, the way we do this is sort of like with a lookup table. So here I have the ASCII table. And what this does is it has a list of numbers with a corresponding character. So the first ones, 0 through 31, are sort of special characters. Those are things like line breaks and white space that you don't really see, but they denote sort of like going down a line. And they're very similar to things you'd have like on a typewriter. So there'd be like line feeds and horizontal tabs, things like that. All the kind of like white space that's in your documents that you don't really see, and still has to be encoded by the computer. More interestingly is what happens after 31. We start getting into the characters. So for example, if we wanted to store the letter A, we'd be storing that in the computer as a number, as a 65. And once we have a number, we already know how to store numbers, so it just stores that as the binary number. So if we wanted to store, for example, an uppercase D, we tell the computer to store the number 68 in binary. And when the computer reads the number 68, if we're interpreting that as text, it goes from 68 and turns it into a D, just using this table. Now, this is a bit of an outdated system. ASCII has now been mostly replaced by something called Unicode, but it's the same exact concept, except Unicode's just a vastly bigger table that includes things like letters in other languages. And they also have a few like special characters, emojis, things like that. So massive table instead of this more limited one. So let's look at an example. Let's say we want to store the word hello, H-E-L-L-O. Now, an important thing to note here is there's a difference between capital and lowercase letters. Remember this table we just saw? You can see that it lists both the capital letters and the lowercase letters, and they have a different decimal value. So we have hello, and we want to store that in the computer. So the first thing we would do is we'd look at our ASCII table, and we'd see that H is 72. So we know that 72 is H, so we'd store a 72. Now you'll see the little 10 subscript here. All that is just denotes that this is a decimal number and lets us know what base it's in, because we can get confusing in some cases. For example, a 10 versus a 10 in binary. So if you see in these notes where there's a subscript 10, that means I'm talking about a decimal number. If there's a subscript 2, that means we're talking about a binary number. So next we want to store the E. We look at our table and we look across and say lowercase e is 101 in decimal. So that's the next value we're going to store. And we do the same thing. We look at the L's. They're both 108 in the table. They're the same number because they're the same letter. And we get the O. That's 111. But remember, the computer isn't storing decimal numbers. It's storing binary numbers. So there is a second step to actually store this in the computer. And that is taking these decimal numbers and now turning them into binary. Now it uses the exact same process we already saw. And we get the binary numbers. So to store hello in the computer, we'd have this massive string of 0100100100111000101, and so on. So it does look like it takes up a lot of space, but each one of these is one of those little transistors. And remember that like a modern CPU has like billions of transistors. So it's not quite a big deal for the computer, although it would be very hard for a human to read. Okay, let's put this into practice with a little activity. I have the word cat written here, capital C, lowercase a, lowercase t. And I wanted you to use what we've learned about ASCII and the ASCII table to turn these into decimal numbers. So don't worry about turning into binary, just the decimal numbers. And there should be 3 of them because we have 3 letters. I'll give you a few seconds and try to do that. And we're back. Let's take a look at the solution. So C should be 67, A is 97, and T is 116. Again, the subscript 10's here, just to note that this is a decimal number and not binary. So how did I do this? Well, I looked at the ASCII table. I looked up capital C is 67, lowercase a is 97, and lowercase t is 116. So a key thing here is remembering that there's a difference between capital and lowercase letters. If we were storing this on a computer, the computer would then go a step further and turn those decimal numbers into binary. So that brings us to our participation activity for the week. What I'd like you to do is come up with a short sentence. It could be any sentence you want. I recommend not doing too many words because that's going to increase the work for you. The more characters there are, the more work it is. And I want you to encode it in ASCII as a series of decimal numbers. Once you've done that, I want you to take those decimal numbers and post them on the course forums under the Week 5 ASCII message form topic. The reason why we're only posting the numbers and not the original sentence is I want to have it so another student will come along in the next step and try to decode your message. So don't post the solution for them. And that brings us to our next step. After you've posted your message, go into the same form topic, look for a post by a student that doesn't yet have a solution, so make sure no one's posted a solution yet, and then decode that student's message. Using the same idea, you go through those decimal numbers and you turn them back into letters. Once you have decoded it, post the solution as a reply. So let's take an example of what this would look like. So come up with a sentence. In this case, my sentence is "One is never alone with a rubber duck." So you can use any sentence except for that one. And then we want to use this ASCII table to convert it. I'll post a link to this table in the video description and in the supplemental information on the OWL tab, but you can also pause the video here and use this one. So once you've done this, go through for each letter, find the number, and come up with a message like this. Then you're only going to post these numbers to the form. Don't post your original message. Now, a few hints here. These are types of questions I usually get from students, are things like, well, what do I do if there's a space? Do I add extra spaces between the numbers? And the answer is no. The ASCII table does have a character for spaces, and that is 32. So wherever there's a space, you should have the number 32. And to make this readable to other students on the forums, make sure you do put a space between each character. So like in the first word we have here is 1. So the O would be a 79, the N's a 110, and the E's 101. And you can see I put a space between each number. And then when we get to the actual space in the sentence, I don't add extra spaces. I just write the number 32 because that represents a space. The other hint I'll give you is that punctuation is also in the ASCII table. So you can see the last character of my message is the period, and that is represented by the number 10. So my message ends with the number 10. You can also use this hint to sort of decode the message or help decode the message, because you know wherever there's a 32, that means that's a space and you're starting a new word. So after you've came up with that and posted it on the forums, just the numbers, then you go and decode someone else's message and post a decoded message as a reply to their post. Try to find ones that don't already have a solution. So we've discussed now how computers can store numbers, and we've discussed how they can store text. But there's a lot more on our computer than just those. What about images, graphics, and videos, things that actually display on your screen? How do computers represent those? Well, we can investigate this with a little bit of an experiment. This is computer science, after all. What I have here is a USB microscope. What we're going to do is I'm going to point it directly at my screen here, right in this square that you can see on the screen now, and we're going to see what we can see. I'll turn it on now. And I'll focus it a little bit. Okay, that looks pretty good. But we have an interesting result here from our little experiment. So we have a little square that we're looking at in the screen, and it's completely white. But despite that, what we're actually seeing are rows of red, green, and blue. So the reason for this is that what we're seeing really zoomed in on are the pixels in your screen. So not each light is a pixel, not like red, green, and blue are each individual pixels. Rather, a pixel is a grouping of 3 of them. So one pixel has 1 red light, 1 green light, and 1 blue light. Now you might be wondering, okay, there's red, green, and blue, but we're looking at white. What's going on here? And the way this works is sort of like a trick on your brain. So the way your eye works, it has 3 different cones in it that detect different colors. Red light, green light, and blue light. When your brain sees all of those at once in one little spot, it interprets that as white. So what's happening here is each spot on our monitor where we have all the lights on full blast, it's coming, hitting your eye, and your eye thinks that because they're so close together and that they're all on full intensity, that this is white light. If they're all off, we would interpret it as black light. If only, for example, the red and the blue light were on, we'd interpret that as purple. So that way we can form most colors that the human eye can see. So let's see what happens when we start changing the color of the square. So I'm going to change it now to red, and we can see something interesting happened. This was white, and this is red. So all of the pixels turned off all the colors except for red, because we only need the red wavelengths to come and hit our eye so we can see it. Now, we're going to turn it to blue, and we can see that all of the green and red lights turned off. In this case, this is a pure blue, so you can see a little bit of green, but if it was a pure blue color, we would get all blue. Next, here's green, and once again, we can see it turned off all of the ones except for green. So it's important to note, even though because we're so zoomed in, we're only seeing a few pixels in the square, they're all changing at the same time. Not all the pixels on the whole screen change to green, because for example, we have up in the corners, we have some white, we got some blue text up there, we got the purple around the box. So not all the pixels on the same screen change at the same time, just the little dots you want to change the color of. So each one can be individually controlled. Let's try another color. This one's yellow, so now it's mixing two colors together, the red and the green. And you might be a little bit confused because you might be used to different color mixing. And when we mix colors, there's two different ways to talk about it. What you sort of learn in kindergarten in grade 1 are mixing paint colors. But when we're talking about light, we're mixing light, so it works a little bit different. So to get yellow, we have red and green. And to get sort of an orange, we just sort of changes the intensities. So we can get quite a dramatic difference by just changing the intensity of the lights, even if the same lights are on. So we have yellow, and now we have a bit of orange. So by being able to individually control each pixel's intensity, how bright the green is, how bright the red is, we can get far more shades of colors than just the basic primary colors and then the first set of mixes. And here's black. So with black, it's a little bit different because it turns everything off. So there's nothing being displayed, and your brain interprets that as black, nothing there. So let's do a little bit of a quick activity here. What I want to do is change this black box to sort of the Western purple color, the same sort of purple that's surrounding the box right now as a border. And I want you to try to predict what are the pixels going to look like if we change this to purple. Which ones are going to be on, and what sort of intensities do you think they're going to be at? You don't have to write it down or anything, but just in your head, try to get an idea of what's going to happen. I'll put up a timer for you to think about it for a few seconds, and then we'll see what happens. Okay, we're back, and let's change the box. And we got a really bright blue and a little dull red. The reason why it wasn't just all red and all blue is because this shade of purple isn't quite like a perfect purple, where it's all red and all blue and an equal amount mixed together. Instead, this is more closer to the Western purple shade. Once again, the intensity of the lights can change the shading and the characteristics of the color. So let's turn off that microscope now and review what we just talked about. Okay, so that was an interesting experiment, so let's summarize. So images, graphics, and videos on computers are stored as pixels, and each individual pixel has a red value, a green value, and a blue value. We actually saw that in the hardware. There's like one little green light, one little red light, one little blue light. And each one of these lights can have a different intensity to it. So it can turn on like all the way, none at all, or somewhere in between. So it's not just binary on and off, it's actually an intensity of light. So how does this get us an actual image in our eyes? Well, the human eye is actually created with cones that are sensitive to each different color, red, green, and blue. And what your brain does is sort of a trick by, depending on what it sees, like if it sees some red and some blue at the same time, it tells you that you're seeing purple. So our monitors on our devices do the same sort of thing. They just output red, green, and blue light, and when you mix that together, your eye and your brain interprets it as different colors. So we can take advantage of that to have graphical displays in computers, phones, and all kinds of things. So now to go a bit more into that, I was saying that each one sort of has a different value, a different intensity that's turned on as. And we represent that in a computer as 3 bytes. 1 byte for red, 1 byte for green, and 1 byte for blue. And the value of that byte determines how intense that color is. So if we had a value of 0 for red, that means the little light would be completely off. We wouldn't see any red at all. If we had a value of 255 for red, it'd be on full blast. So why 0 to 255, not like why 0 to 1,000 or something, or 0 to 100. The reason why is a byte on a computer is 8 bits. And using that method that we saw before of converting bits into a decimal number, the largest number you can get when you have 8 bits and you're talking about positive numbers is 255. The number 0 to 255. So since we only have 1 byte for each, that means the largest number is 255. So to summarize, the values are turned into light and mixed together to form a single color. To give an example, we have here the red value of 79, a green value of 38, and a blue value of 131. And that gives us this sort of shade of purple that we see on the screen here in that box. The only reason why this color is significant is that's actually Western's official purple color. So in the actual Western documentations for branding, they actually specify each light value for red, green, and blue for what the official Western purple is. And for businesses, this is kind of interesting because in some cases you actually can trademark a color. And when you're doing that, you're going to have to know exactly what shade of color it is. Though that is a bit of a tricky legal matter, so I won't go too depth into that because it's out of my field, but there are cases where businesses actually do have trademarks on a specific color. And the way they would specify that, again, is probably in this red, green, blue system. Now, if you've ever done web development or worked with things like Photoshop, you often see these colors represented in a different way, usually in hexadecimal. So we saw decimal, those are the numbers we use already, at base 10, what you can count to on your fingers. And we also saw binary, that's just ones and zeros. Hexadecimal is a similar idea, except it's a base of 16. So that means we have the numbers in one place all the way from 0 to 15. Now that might be a bit confusing, like how do you represent the number like 10 or 11 as its own digit? Well, in that case, you start putting in letters. So 10 would be an A, 11 would be a B, and so on all the way up to F for 15. You don't have to know the details of how hexadecimal works for this course, but you should know that it is often used to represent colors. So the exact same color that we have here, the purple, could also be represented in hexadecimal as 4F for red, 26 for green, and 83 for blue. The same number is just represented in a different way. We also sometimes see the decimal representation, sometimes with brackets around it, like RGB, bracket, and then the same decimal numbers we've seen. Okay, so moving on a bit, we have seen that individual switches are the bits in our computer's memory, but we also have names for different size chunks of bits. A group of 8 bits, like I just mentioned, is called a byte. That means if you have a file that is 100,000 bytes in size, that has 800,000 bits, as each byte is 8 bits. 8 bits is a significant number, as this is how many bits we need to store a single character of data, such as we saw from our ASCII table. So you can sort of think of each byte in a computer as a single character on your keyboard. Though it doesn't have to actually be representing a character, like we saw we can do a number, but we can think about a byte as storing a single character. We have names and prefixes for different numbers of bytes as well, and these are commonly used when talking about storage capacities of memory. These closely follow the SI units, like you see with other measurements, except the values are slightly different. You can see here that a kilobyte is 1024 bytes and not 1000 bytes, as you might expect. When you go from like a meter to a kilometer, you have 1000 meters. But in this case, we have 1024. The reason for this is a bit complicated, but we already have some hints at it. Recall that each switch was labeled with a power of 2. We had 2 to the power of 0, 2 to the power of 1, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and we just keep on going for how many ever bits you have. Well, 10 to the 24 is a special number. It's 2 to the power of 10, and that is the closest power of 2 to 1000. And this is why these are all sort of offset a bit from what you'd expect for SI scientific units. For our purposes, I don't expect you to memorize all these numbers about how many bytes each one it is. Rather, I want you to understand this in more practical terms, as this will be far more useful and important to you when you go out into the real world. I want you to know exactly how much you can store in practical terms, like how many movies, how many photos, for each one of these units, as opposed to telling me that like a megabyte is 1,048,576 bytes. So let's take a look. A byte, as we already mentioned, is a single character. So that could be like a single character on your keyboard, like the capital A, or it could be punctuation, things like that. But that can also represent a number. So a kilobyte is approximately a single page of text. A megabyte is about a minute of music, or 250 pages of text, sort of like a short book. A gigabyte can store just over an hour of HD video in 720p or just under an hour in 1080p videos. Those would be the resolutions of the video. And those would both be different HD formats, but not quite the newest 4K format. A terabyte can hold about 250 HD movies, depending on the resolution and quality, or about 10 of the largest PC games out there right now. Petabyte is where we start getting out of the range of the home user, and this can store about 11,000 4K movies, or 20 petabytes, if we had that instead of just one, would be enough to store the whole Library of Congress from the United States. An exabyte is where things start getting ridiculous. This could store all the words ever spoken aloud by mankind up to this point in history as text, or a video that's over 237,823 years long. So amazingly, there are actually some companies today that have over an exabyte of storage. They mostly use this for cloud computing or big data use cases. Remember, businesses want to track everything, and when this is taken to the extreme, we need extreme storage. Zettabyte could store all the internet traffic in the world. At least it could have before 2016. Now we're transmitting far more than this. So if you wanted sort of like a snapshot of all the data that's currently in transit on the internet, you would need over a zettabyte of storage. That just gives you some idea of just how much data we are pumping through the internet at a single point of time. The reason why this is possible is we don't necessarily have to store all that data that's being transmitted. So as a last topic, I'll mention how new hardware can affect competitive strategies. There are three big hardware developments we are seeing that have significant disruption potential. Recall that disruptive technology are the ones that have the potential to change the shape of an industry, sort of like how Netflix changed the shape of the video rental industry. These are the Internet of Things, or IoT for short, self-driving cars, and 3D printing. Now, I've already covered 3D printing in our Chapter 1 lecture, and I'm sure you're sick of me going on about it by now, so we'll just briefly cover that one and mostly look at the other two, IoT and self-driving cars. The Internet of Things is a trend we are seeing to embed network and sensor hardware into electronics that would traditionally not have them. This enables them to connect to a network or the internet to share this data, as well as enable remote control over the device. When combined together, these objects allow for more complex and interesting interactions. This has largely been made possible through miniaturization of chips and the rapid reduction of their costs. So what I'm showing you over to the side right now, should be this, is an ESP8266. Actually, it's not the whole thing, is the ESP8266, but just this small little chip right here. Now, what's amazing about this chip is that it is not only a fully programmable microcontroller, but it also has Wi-Fi and networking capabilities. Now that's kind of impressive since it's something as small as a dime. This chip cost me under $3, and if you were buying these in bulk at wholesale, you could even get them for a few cents each. With Wi-Fi capabilities in a package so small and cheap, it's becoming trivial to add internet connectivity as a feature to new electronics that traditionally would not have it, or need it. So for companies, something like this ESP makes it really easy to differentiate your product. You could be making, for example, a cat feeder, or a thermostat, or a scale, and you'd have the option of just for $3 at worst case per unit, you could make it internet or smart scale, or internet or smart cat feeder. So it is really appealing to companies to throw in that little extra benefit because it costs them so little, and it provides it as like a different product in the marketplace, and one that's even seen as more like high quality or professional. So I did mention, for an example, throwing one of these ESPs into a cat feeder, for example, to make it a smart cat feeder. And that's not just completely a silly example, it's something I've actually done as a hobby project. I'll show it over there to the side, but what I did is I just bought a cheap cat feeder from pet store that was just sort of dumb, I just worked on a timer, and I threw in one of these ESP chips with a bit of circuitry, and now it can be used over the internet to feed cats. So it might not be that impressive to look at, but it is an example of what even just like a home hobbyist could do with one of these chips. So for companies, it's now quite easy to make anything they want, connect to the internet, and be sort of a smart device rather than an old dumb device. More common off-the-shelf examples of IoT devices, these would be things that you could actually go into the store to buy as opposed to make yourself, would include things like smart plugs, like I have right here. And these are power outlets that you can control over the internet and can report your power usage in some cases. So you can plug something in there, and now it sort of like makes it a smart device by being able to control if it has power or not, and also get an idea of how much power it's using. More examples would be things like smart light switches that can turn lights on and off, or in some cases dim them, and that can all be done remotely through an app or over the internet connection. Another example would be smart thermostats, and these would be thermostats that control the heat or temperature in your house, except they would be controlled remotely over the internet or through your network. And even smart security cameras that will notify you if they detect movement live over the internet and allow you to talk through the camera. There are, however, security risks to consider when connecting real-world devices like this to the internet. There are few standards for security in IoT devices, and even less that are followed today. It's up to the device manufacturer to properly secure both the devices and the cloud that runs them. And unfortunately, we often see them failing to do this properly. This is a scary thought when you consider that these devices have real-world impacts, such as someone watching you through their security camera, or even changing temperatures in your house. And we're back inside. And there are many, many more examples of IoT devices that we could talk about, such as smart locks, leak detectors, security systems, smart TVs, smart refrigerators, home assistants, and so on. The list is almost endless. And these devices can be interconnected so we can do things like ask Alexa to turn on the lights, or Siri to play a show on our TV. As an example here, I'm using a Roku Smart TV, and I'm telling it to put some different shows on. Play Star Trek: The Next Generation on Netflix. Stop and go home. Complex interactions can also be created, such as turning on the lights when you get home, or only using a dehumidifier when the power rates are cheapest. And this is actually one that I do myself and what I use most of my smart plugs for. I have them set up with my dehumidifier and air purifiers so that when the power rates drop lower in the evenings, they turn on, and when the power rates start going up in the mornings, they turn off. So a lot of these IoT devices are actually based around energy savings. Things like smart thermostats, power plugs, light switches can all be used to help improve our energy use by sort of disabling them when they're not needed or disabling them when demand is higher. Beyond home consumer use, we also see a lot of IoT devices in industry and business. IoT-based sensors, for example, provide a means to keep a close eye on production and better monitor things like raw material use and employee productivity. IoT devices in the office environment are also useful, as they can be useful for saving energy by shutting off lights, cooling, or heating when a space is not in use. For example, you might have an IoT motion sensor that detects motion in an office, and if it stops detecting motion, it starts shutting the lights off and reducing cooling and heating to save on energy. And there have been some case studies of this, such as with Microsoft, who are able to save quite significant amounts of money by implementing these sort of smart sensors. Next up is self-driving cars. Now, unlike IoT devices, these are not quite a reality yet. At least not full self-driving cars, where the human never has to really interact with the car at all. However, there is a significant potential for disruption in multiple industries if self-driving cars are ever fully realized. Self-driving cars could completely change transportation as we know it. Rather than owning a car, you might just have a service like Uber that sends a self-driving car to your location by itself, with no human inside. You get in, and it takes you off to your destination without you even needing to touch the steering wheel. So there's no need to find a parking spot when you get there, you just get out, and it drives off to the next customer. This could also be very disruptive for the shipping industry, if trucks and packages could deliver themselves, for example. Also, the reduced number of accidents and having fewer people now owning cars in favor of these services could also have a dramatic impact on the auto insurance industry. Less cars could mean fewer car sales, and the ones that are sold would be sold to businesses rather than individuals. Similarly, the need for car mechanics and tow trucks would be forever changed. As individuals would not own their own car and instead use services, like Uber for example, mechanics and tow truck services would likely move from being independent businesses or businesses that are part of the car company to being part of larger car service companies like Uber, or as just service contracts between two businesses. Self-driving cars would also increase demand for jobs like engineers, programmers, and system designers, as well as increasing demand on hardware like sensors, cameras, and batteries. In fact, we're also seeing a rapid demand on batteries and the metals that make them, just because of the introduction of electric vehicles. There are a lot of limitations to consider here, however. First and foremost, this is all science fiction until someone can produce a fully self-driving car. There's been significant advances in things like highway driving, staying in lanes, and even AI to handle parking. However, these alone are not enough to be truly disruptive. For that, we need a self-driving car that can complete a whole trip, not just highway driving, and be able to be as at least reliable as a human driver. And we're just not there yet. As future business owners, we should be aware of the disruptive potential of self-driving cars, and at the same time be skeptical of claims that they'll be available in the near future. So for example, it might be a bad idea to start a taxi company, but at the same time, it would also might be a bad idea if you're a shipping company to assume that you're going to have self-driving cars or self-driving trucks in the near future. Another potential issue is who will hold the legal liability for all this if it goes wrong. By this I mean, who will be at fault when a self-driving car is involved in an accident, speeds, or breaks other traffic laws? Will it be the car manufacturer, the human inside the car, or the business or individual that owns the car? Currently, there's not really a clear answer here. Last but not least is 3D printing. We already covered this pretty extensively in my Chapter 1 lecture, but as a quick review, 3D printing allows for rapid prototyping by taking a 3D model and turning it into a real-world object. It does this by melting 3D printer filament like this, which is sort of like a big spool of plastic string, and putting it in layers to make a real-world object. So this has also been used beyond rapid prototyping in things like printing customized orthotics and dental implants. For the home market, however, the cost of 3D printing is rapidly dropping, and it is now reasonable for home enthusiasts and hobbyists to purchase a 3D printer, but there's still a bit of maintenance involved in them, and it can be a bit complex for your average home user. So we might not see widespread adoption in the home market for some time yet. 3D printers also have limitations in what they can print. While some fancy research-grade printers can print things like electronic circuitry or even organic compounds, these are largely experimental and not yet ready for industrial use, never mind home use. So most 3D printers primarily print plastic, though we do see some that print metal or ceramic, and they're unable to create that sort of electronic components or non-plastic parts of an object. So we're not going to be able to print a whole computer or a cell phone or something like that, but we could do something like print the case of it. They also tend to be slow and not very scalable compared to traditional methods like injection molding, making them ideal for rapid prototyping and one-off products, but not mass manufacturing. So that's all I have for you in this video, but we're not yet done with Chapter 4. We continue on with Chapter 4 in our next video on software. Have a break, grab some snacks and a drink, and start watching that software lecture. Thank you for watching, and once again, have a great day.